Hello, good morning. Hello, hello, yes. Alrighty. Good morning. How's everyone doing? Choo, choo, choo. Computational design, computational design, computational design. Hoo, hoo. All right. As you can see, I've had a lot of coffee before showing up here today, so you're gonna have to deal with that. All right. I am having small technical problems, so if you forgive me, I still need to set up a couple things. Basically, I need to set up the computer that I use for sketching, for like drawing doodles and stuff, which I'm going to be using today. And my Windows has decided to self-update on its own, and it's taking forever. And I hope it finishes before midnight today. Um, yep. So that's where we are. How's everyone doing? Anya, I'm not sure how to pronounce that, but welcome. Mohammed, is that an abbreviation for Mohammed? Hi, welcome. How are you doing? Well, 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 well. And how am I doing? I'm doing fine today. Um, I am, well, except for the fact that my computer has decided to not join us today. But hopefully that will change very soon. Um, what do we have today going on? All right, I'm going to give folks a couple minutes to get set up, work on, get set up. I also kind of, wait. I wanted to check something out, actually. And there you go, this stuff. Okay, all right. Um, hmm. Yes. Sorry, I'm still setting myself up mentally. Also, I'm sorry. What? It started again? No. Still. You see? No good. No good. Oh my God. Okay. Well, we're gonna need a few minutes. I'm sorry for this, and sorry for not announcing the live stream ahead of time. I kind of took a little bit of time off this weekend. I moved into a new apartment, so I'm cleaning my apartment. I am buying furniture. I'm doing all those like household thingies that you do. And I'm kind of excited about that. So yeah, I've had a homely weekend, so I didn't catch up with emailing stuff. Simon, good morning. How are you doing? So Thivas, hey, what's up? Welcome back. That's how you doing? All right. Oh, hey, it's back. Wait. Hold on. Good. So let me try if this actually works. So I'm going to connect to a wireless display. That should be, and of course it's not working. Wait, let's give it so okay, they're both on the same. Are they both on the same network? Yes, they are. So okay, and then I'm going to try to connect to this thing. Yes. And so if I do, wait, if I open my sketchbook here and I do this, I can draw, right? Oh yeah, great. Okie dokie. So that sounds good. So I'm going to go back to, well, let me set this up on the table. Give me 1 second. I know I should be more ready for these things, but what can I say? You know, sometimes you wake up and things need a little bit of preparation. Okay, and then where am I? Where is my mouse? Here. I'm going to move this up here, and I'm going to move this other thing up here, so I can. Hey. Aha, how's that? Alrighty. I think we're ready. I'm think I'm ready on my side. Whoa, 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 whoa. Or like more like a whoa, 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 more like elegant. Okay. Oh, I should probably move myself to the other side here, just to match with the other videos. No? Because like here, when I'm doing here, what is my transform? And the transform is 600. So when I do this, the transform should also be 600, I guess, right? Yes. So now I can do this and switch seamlessly. Very nice. I like this. And I'm going to move these two things here. Do I need these things actually? Do I ever use these things? I don't even use them, right? So yeah, out. Okay, fine. And then okay. All right, so I'm here and I'm going to fire some Rhino. No, Rhino 6. We're doing Rhino 6 today so that we are a little more cross-compatible with everyone else who might be still behind. And I got some Rhino here going on. Yes, and I got my grasshopper going on, which, oh, you can't see really right now, right? Because I cut you out. Okay. All right. All right. Oh, Yasharj. Thank you for your words and thanks for being here. I think it's a wonderful place too. But thanks for being here. Salvador, good morning. And Sotivas, yes, we're continuing with the introduction to parametric modeling series. So, I forgot to say, well, now that I'm ready, welcome everyone. I'm very happy to be here. I'm very happy to be sharing this time with all of you. And I want to make sure that, okay, wait. Yes, I want to make sure that we are all properly introduced. My name is Jose Luis. I run this thing called Parametric Camp. We do live streams about computational design. I teach tutorials on how to code, how to do parametric modeling, how to do computational geometry, and all these cool things that use technology to make us more creative and more and help us express things, you know, design-wise. We have a lot of social media. If you want to follow us, if you're interested in what we do, please subscribe to the channel and turn on notifications so that you know when we go live stream. Otherwise, you can always follow us on any social media or on YouTube. What we do is we record tutorials here live in the live stream, and then what we do is like we chop them, we edit them, and then we publish them as refined videos for those people who don't want to sit over 2 hours of me going back and forth, blah blah blah, which I would totally understand. I don't think I would do that for anyone except for Daniel Schiffman, maybe. So, and also for those of you who wanna stay closer with us in the community, we have a Discord channel that we use to keep communication live over the week when we're not streaming. So I just posted the link on the chat right now, and you're welcome to go and sign up for the join the server. There's a channel called Introductions. So if you wanna go there, we have a template for like writing your name, what your interests are, how did you get to know about us, etc., etc. It's a really nice way for all of us to get to know each other. It's also a really good way for me to understand who you are and why you're interested in joining us. Yeah, as I said, if you want, please subscribe to this channel so that you get notifications when we go live. And we also have a calendar, a Google Calendar that you can join and where I post when we go live. So that's it. And what we're doing is we typically stream on Fridays. And we typically do 2 live streams, one in the morning. I'm in the East Coast in the United States. So we typically do one in the morning, 10 a.m. my time, and another one in the afternoon, 2 p.m. my time. But this week is going to be a little special because we had a playlist of tutorials that was Introduction to Parametric Modeling that I had forgotten and neglected to do for a very long time. So I decided that we're gonna grab this thing by the reins, and this week we're going to do an intensive live stream thon where I'm basically going to be streaming every day, in the morning and in the afternoon. Hey, and we have Nono here with us. How are you doing, sir? Welcome, welcome to the channel. Again, Nono is a really good old friend who also, by the way, where are you? Let me fire up. So, who also, by the way, has his own YouTube channel that I would like to recommend to you right now. This one. So if you Google YouTube/Nono Martinez Alonso, I just posted that in the chat. He has a super interesting YouTube channel where he covers a lot of topics on, specifically, he's been doing a lot of machine learning lately, but he does also how to create cloud services, how to do Amazon web stuff, and he also runs the Getting Simple podcast. For those of you who may not know, but if you go to Spotify or wherever you take your podcasts, you can search for the Getting Simple podcast, and you can hear a lot of podcasts about that he does where he interviews people and he asks them about their way of living, the way they approach life, the way they work, and good habits that maybe lead to simplicity and how to streamline work. I'm actually in the middle of the thing, sorry. But yes, so you definitely want to check this out. Yours truly has been lucky enough to be interviewed a couple times here. So if you want to hear me ranting about the robots and creativity and blah, 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 I also have a couple of episodes here somewhere as well. But you definitely need to check out these tutorials. They're really, really cool. Okay? Alrighty. And is that a good description, Nono? What do you think about that? I hope I didn't misrepresent anything. Anyway, where were we? Yes, today, what are we doing? We are continuing with the Introduction to Parametric Modeling playlist. And I had a list of things that I wanted to cover here. So I think today we're going to start with Introduction to NURBS Geometry. And we're going to do that. How are we going to do that? We're going to do that. How are we going to do that? That's a really good question. Okay, so yes. So today we're going to do 2 live streams, one in the morning, one in the afternoon, and then the one in the morning, we're going to touch upon NURBS geometry. So I'm going to be explaining what NURBS geometry is, how it works, the basic properties of things that you need to keep in mind, and what else? And then we're going to do a few exercises. We're going to do a few exercises with lines and polylines and splines and blah, blah. We're going to discuss how to import geometry from Rhino into Grasshopper, which is something that we haven't seen yet. And then hopefully, if we have time, we will end up with NURBS surfaces this morning. But if we don't, then we will do that in the afternoon. So remember, we're streaming at 2 p.m. again today, 2 p.m. my time, so East Coast in the US. And in the afternoon, we're going to be doing a bunch of exercises. So practical exercises. All right. How does that sound? Does that sound like a plan? Are you excited? Can you give me a hands up? Choo-choo, choo-choo. Yes, I should not be drinking so much coffee before I do these things, because then things happen. Okay, so NURBS geometry. What do I want to say about NURBS geometry? What do I want to say? What are we going to say? Well, I'm going to do some sketching here. So I will draw some stuff and I will explain things. But I probably want to start first by explaining or showing what NURBS geometry is. NURBS geometry. What are NURBS? Actually, well, NURBS geometry, blah, 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 control point, not some control points. Maybe this could be interesting. Wikipedia. I want to recommend Raja Isha's Intro to Mathematics for Computational Design. I probably want to recommend Essential Mathematics for Computational Design. Here. Position vector, vectors of a point. Previewing position vectors, unit vectors, blah, blah, blah. Ah, I didn't know she made all these videos. This is pretty cool. Okay. So we're going to recommend that definitely. Okay. I'm going to show this. All right. I'm going to show that here probably. And then here, I want essential mathematics for computational design. Yes. And this is not very neat, actually, so I'm going to remove this here. Okay. Oh, and here, what was I going to do? Okay, so, all right, so I think we can start this video. This one, my first one is a little more theoretical, so it might be a little bumpy as we record this. So, what are we going to do? I'm going to start with NURBS. Actually, this is a pretty nice drawing. I can probably use these drawings when I explain things. Meshes versus NURBS. It's a pretty nice drawing too. This is a pretty nice drawing too. Hmm. Coloring chaos. What is this? Okay, I'm getting a little NURBS surfaces and concepts. I can probably show that later. Okay, sorry I'm ranting a little bit, but I want to think this through before I start recording. Okay, we can just start. Let's just start. Hi, this is Jose Luis, and welcome to this new video, which is part of the larger series of. No, out. Let's start over again. What am I going to say? It's part of. And welcome to this new section in the list, in the playlist, the Introduction to Parametric Modeling series. Okay. Should I explain first as opposed to other forms of should I explain as opposed to other forms of geometry or Euclidean geometry? I just don't want to make it. What am I going to do? What is going on? Why? Let's just do it. Great. Let's move on. Hi, this is Jose Luis, and welcome to this new section on our playlist of on our no, it's not a playlist. Is it a playlist? Welcome to this new section on our series. Yes, exactly. Hi, my name is Jose Luis, and welcome to this new section in the series Introduction to Parametric Modeling, where we're going to discuss different types of geometry and how they affect. No, no, I'm not going. How they affect now. We're going to discuss in particular NURBS geometry. We're going to discuss NURBS geometry. That's what we're going to do here. Okay. Hi, this is Jose Luis, and welcome to this new section in the series Introduction to Parametric Modeling, where I would like to take a closer look at a type of geometry that we're going to be using very often in parametric modeling, which is NURBS geometry. And what do I mean by that? Well, it turns out that when it comes to geometry types, if you will, there are we can oversimplify the situation by saying that there are a bunch of different families of geometry types that we can use when modeling in three-dimensional environments. And if you come from other environments, you might be used to simpler entities such as points, lines, vectors, and even meshes. Meshes being a representation of a 3D object that is faceted with small triangles, right? However, in parametric modeling, there is a family of geometry types that is very, very commonly used, which is called NURBS geometry. NURBS geometry stands for non-uniform rational B-spline, which is a big mouthful, But basically, it is a way of defining geometry so that instead of being defined just by the Cartesian coordinates of the points that define that geometry, we can think that the representation of the geometry that we do with NURBS geometry is, instead of being discrete units in three-dimensional space, they are continuous representation that have I'm not sure I am happy with what I was saying, so we're going to start over again. We're going to start over again. I don't know what I was getting there with that. Okay, so let me start over again. Hi, this is Jose Luis, and welcome to this new section in the series Introduction to Parametric Modeling, where I would like to take a closer look at a particular type of geometry that we're going to be using extensively here, which is NURBS geometry. And this is very important because if you're coming from other modeling environments where you have used points, lines, and maybe meshes as three-dimensional representations of form that are discretized in triangles in three-dimensional space, NURBS are a little different. They are radically different because what's important about NURBS geometry is that it is a mathematical model to describe geometry that relies on functional representations. Okay, no need to get into the weeds of what that actually means, but in an oversimplified form, in an oversimplified way, what that means is that when we work with NURBS geometry, as opposed, for example, to meshes that are basically discretized partitions of three-dimensional space, with NURBS, because there is no discretization based on triangles or based on points, but there is a mathematical polynomial, like a complex polynomial that is defining the shape of a curve or of a surface, then it turns out that there are many advantages to that. One of them being, for example, the fact that we can generate free form like geometry that has no discretization, that is infinitely smooth. Okay, we're going to keep that one. And then I'm going to think about where do I want to go next with the description. That is infinitely smooth. So what do I want to do now? Okay, so I probably want to talk about how do we control these things. Anyway, I was saying it's infinitely smooth. This model has a lot of advantages. So as I said, we can create smooth curvature, and the way we interact with the curvature with the form gives us an interface to modeling that feels very free form. So as opposed to how rigid sometimes working with meshes can feel, and at the same time, there is a lot of interesting properties that we can extract from NURBS geometry to manipulate it parametrically as well. So it's actually a pretty interesting model. And just as meshes, for example, are extremely common and super popular in computer graphics and other applications such as digital fabrication, etc., NURBS are actually super popular when it comes to environments that need super fine control of curvature for whatever reason, such as, for example, aerospace, or such as, for example, automotive, or such as, for example, product design and jewelry. And it's a very interesting one. So in this video, I would like to explain to you what are the basic properties of NURBS geometry, how do we control it, how do we work with it, and some concepts that we will need that stem from the fact that NURBS geometry has a mathematical model behind it, and why those properties will be important in parametric modeling. So stay here with me. Let's go to the whiteboard and let me explain to you a couple things. Alrighty, so whiteboard. So what are we going to do? Should I actually draw stuff here? Where are the layers? Here, okay. I'm going to draw stuff here. Ali Chandra, how you doing? Arasto. My parametric design teacher compares NURBS versus mesh geometry to vector and raster images. That is a pretty good comparison, actually. Okay, so should I draw stuff first? I can probably draw stuff first, right? Yes, so let me draw some stuff first. So let's say that I have this curve. Oh, that's not a great curve. What if I use this guy? Nope, I don't like that either. What if I draw with this one? And what's the difference between that one and this one? Oh, nope. I want something thicker. Okay. Brush properties, type marker. Okay, you can see, I don't think you can see my UI on the recording. All right, so if I do this, okay, so how about this? So this might be a curve, okay? And then I'm going to now draw on a new layer. I'm going to draw control points. I'm going to draw a control point here. I'm going to draw a control point here, control point here, control point here, and control point here. Those are really bad control points, right? Oh, God. Okay, so how about this? Control point, control point, control point, control point, control point, and control point. And then for this one, I'm going to do light gray. So that's going to be, no. And that's going to be a new layer. And it's going to be this one, this one, this one, this one, and this one. Actually, this one, I would like this to be tangent here. And actually, you know what? I'm going to remove these two because I'm going to move them a little lower, and I'm going to, this is going to be here. Okay, and then I'm going to go back to here. I'm going to go back here, and this one, and this one. And I'm going to change the order of the layers like this. Okay, for example. So that can be one thing. All right. Okay. The Discord invite is not, it's invalid. Oh, okay. So let me share another one. Well, I see people joining today. Some people just joined. Someone just joined 2 minutes ago. Huh. Okay, but I can create another link. That's fine. How about here? How about this one? No, it's the same one. Yeah, it's the same one. That should work. Let me know if it doesn't work, Denise. It should definitely work. Okay. So how are we going to explain NURBS geometry? Well, we're going to start with control points. Then we're going to do the domain of a curve. We're going to do the domain. And then the degree. Hmm. Okay. And I think you probably want, if I draw anymore, I probably want to draw with red, for example. Okay. All right, so let's do this. Let's start with the basics. So imagine we have a NURBS curve, which has some kind of free-form geometry like the one that I just have in this sketch here. One of the first and most important properties of NURBS curves, and probably the one that we actually use to generate NURBS curves typically, is what's called the control points. You can think of the control points as a family of points that defines the overall shape, the overall curvature of the B-spline. Okay, what does this mean? Well, it turns out that for reasons that we're not going to get into much, one of the main ways that we have for defining NURBS curves is this family of control points, because these control points, the coordinates of where they are in three-dimensional space, are the ones that define the parameters and of the polynomial, the mathematical polynomial that is defining this curve across space. And it turns out that in 3D modeling environments, we will see that on the next video, as you can create these points in 3D space, and you can drag them and move them around and adapt the shape of the NURBS curves by using what's called the control polygon. The control polygon is just simply a way of representing with a polyline, representing how we can unite all these control points together to represent the bounding box. This is not the right term, but to represent the control polygon that drives the form of this curve. And we're going to start over again here because I think I got a little messy. So we're going to start over again. This list is very important for me, so I really want to get it right. So if it's going to be a little slower perhaps than other videos or other series that we do, because I really want to get this one right. Let's start with the basics. So let's imagine that we have created some kind of NURBS curves in three-dimensional space, and it looks something like this. It's a free-form, very smooth curve that lives in three-dimensional space in, for example, Rhino or whichever other 3D model environment that supports NURBS geometry is. One of the main properties, probably one of the most important ones of any NURBS geometry, is its control points. And actually, the control points are typically the most common way of generating NURBS geometry. The control points is typically a family of three-dimensional points it's a family of points in three-dimensional space that define the overall shape of the curve. Altogether, if we join them with a polyline, they form this thing that is called the control polygon. But the control polygon is just a polyline that basically joins all these control points together. What's important is the coordinate of those points. And what happens is that this control polygon, you can think of it as the skeleton that defines the overall shape of this curve. And it turns out that, as we will see in videos very soon, When you move these points in three-dimensional space, you can actually tweak and adjust and notch the overall curvature of this curve, right? Now, we're saying this because if you remember, I said that NURBS geometry is based on a mathematical representation of geometry that has an underlying really large polynomial that defines where each point on this curve lies. And it turns out that these control polygons are the ones that give parameters to this polynomial so that we have the functional representation of the geometry. What that means is that where those points are in space changes coefficients in the polynomial, the mathematical representation of this curve, and that's why we adjust the curvature in three-dimensional space. But that polynomial also has other things that affect the curvature of the geometry. So for example, there's another concept that is very important in NURBS geometry, which is the degree of the geometry. What does that mean? Well, it turns out that, for example, a typical NURBS geometry out of the box in most 3D modeling environments, and Rhino is an example of this one, out of the box, they have a degree of 3. What that means is that the polynomial that represents this curve, the maximum exponent of any of the parameters of the curve is level 3. It's the degree 3. It's a cubic polynomial. And the degree of the curve, what gives us is a representation of how smooth that curve is going to travel through the control points. What does that mean? What it means in practical terms is, imagine I have this curve and this curve is degree 3. If I were to change the degree of this curve and make it degree 2, then we will have a kind of curve that will snap closer to the control polygon, something like I have drawn there. And actually, because it's degree 2, each one of the segments happens to that it will be tangent here to the control polygon, something that did not happen with control 3. And also it happens that each one of the segments will be a cubic curve, a quadratic curve, basically degree 2. Now, if we reduce the degree one more level and we have a NURBS curve of degree 1, it turns out that all the segments are polynomials of degree 1. And which geometry can be represented with a polynomial of degree 1? Well, it turns out that is straight lines. So a NURBS curve of degree 1 is basically a polyline. It's something that looks like this. All right? So the lower the degree of the curve, the closer or the more bound the curve is to the control polygon. Whereas the opposite is also true. If we have the red curve, which is degree 3, and then we increase the degree, then the curve will travel even more smoothly throughout the points. So a degree curve might be something like this, degree 4, and degree 5 would be even smoother, maybe something like this. Okay? So, as we will see very soon, if you want to play with the degree of a curve, the higher the degree, the smoother it will go through the control polygon. You have to remember, though, that one of the rules of NURBS geometry is that you need one more control point than the degree of the curve. So if you want a curve of degree 5, you will need at least to have 6 control points in your curve. Otherwise, you just cannot generate that. Okay, that one was good. I think we're going to keep that one. And I think I want to explain the domain of curves now. The domain of curves. So how are we going to do that? The domain of a curve, what we're going to do is I'm going to clear the screen up and I'm going to explain that curves have mm-hmm. Oh, I do want to say that I want to recommend people to check my YouTube channel. My YouTube channel with the lectures here, where are here? Oops, oopsie. Curves. Is this where I speak? Where I talk about? No, this is not the one. I think it's this one where I talk about curves here, NURBS geometry, right? Is it this one? I think it's this one, yes. Yes. Okay. I will show that at some point. By the end of the video. Okay. And then we're going back here. So now we're going to explain the domain. And for the domain, I may want to say something like, do I want to get into that? So for example, what if I say, it's the domain, it's ax3 plus bx2 plus cx plus d equals 0. Actually, if I'm going to do that, why not just use t? Okay, maybe. Maybe. And then okay. All right, so now okay. And yes, I just added a few notations of which degree each one of the curves that I just drew has here. Okay. And now one of the last properties of NURBS geometry that I would like to talk about, and it's extremely important, is the concept of the domain of a curve and the concept of finding parameters along that curve. What does that mean? Well, let me turn off all these control polygon, all these different lines, and let's stick to the curve that we have at the center, which we have defined that by definition is going to be of degree 3. What that means is that, as I was saying before, there is some kind of polynomial underneath. There is some kind of mathematical representation that looks something like that. It looks like a polynomial where that depends on an unknown variable called t in this example. And yes, those are t's. My t's are a little special. And then it has some coefficients, a, b, c, d, whatever, which depend on the coordinates of the control points. And it turns out that t is typically a parameter that tells us no, I need to start over again. That was not going well. What did not go well? I got into the weeds of so what I can say is that polynomial, if I plug in different values for t, 0, 1, 2, 3, 4, then what I can find is all the possible points in x. Okay, all right. Okay, so I think that's what I want to say. Okay. And yes, I have added a few annotations here on the diagram about which degree each one of the curves that I have drawn has. Okay, so you can see from smoother, which is 5, to basically a polyline, which is number 1. So no curvature at all. And then the last property that I would like to discuss of NURBS geometry is one that is extremely important, which is the domain of a curve and the idea of finding parameters, finding points across the domain of that curve. What does that mean? Let me turn off all these different degree curves, and let's stick with the main one we had, which, as we said, was of degree 3. What that means is that, as I was explaining before, there is some kind of polynomial that the software is handling for us somewhere, which looks something like that. It depends on an unknown variable. In that case, I have called it t. And yes, those things that I have there are t's, my t's are a little special. But it also has some other coefficients, a, b, c, and d, which are numbers that we know because of the control points. So the control points define which coefficients do I have in that polynomial. What that means is that that equation is the one, that polynomial is the one that drives the shape of the curve, more or less. This is not exactly like that, but more or less. And the unknown parameter t is the one that defines where along the curve we can position ourselves. What that means is that because the only thing that we don't know there is t, if we start plugging in values to the parameter t, so for example 0, 0 0.5, 0 0.8, 1, 1.5, 2, whatever, and we solve the equation, we can find the coordinates of a point along a particular length of the curve. So that concept is typically represented as the domain of a curve. The domain of a curve is the idea that there is some kind of range, numerical range embedded in a particular curve that defines where the curve starts and where the curve ends in that polynomial. And which means that any value outside of that is not part of the curve. Because remember, polynomials are infinite. So we have to segment that. So very typically, curves may have a parameter that starts, for example, at the value of 0. Maybe that's not always guaranteed, and can end in whichever value. So for example, the value of 23 or 23.45. It doesn't really matter, right? It will never be guaranteed that it's something from 0 to 1. Only lines have a parameter space, have a domain that goes between 0 and 1. And then what that means is that for any number within that domain, within 0 at 23, I can find a point line on that NURBS curve that corresponds to that parameter. So for example, if this was the equation that represents this curve, if I plug in here the number 5, then the equation will probably give me a point that lies somewhere here, maybe, more or less. I'm totally eyeballing this one. Or if I give if I give this equation the parameter t equals, I don't know, 22, it will probably give me a point that is very, very close to the end of the curve. And if I plug in here the value of 0, it will give me the starting point. For the value of 23, it will give me the ending point. And for a value of 11.5, it will probably give me a point that is somewhere close to the center of the curve, but is not guaranteed to be the exact center of the curve. Because, for reasons that I will explain later in this series of videos, the domain space is not evenly distributed across a NURBS curve. And actually, why do that later? Why don't we just do that now? Let me explain to you why that's the case right now. So let's do that. So I'm going to do that right now. So I'm going to create another curve. This one is going to be, so the control points are going to be this one, this one, this one, and something like that. And then the control curve is going to be something like, oops. The curve is going to be something like this. The curve is going to be something like this. And the control polygon is going to look something like this. All right. Okay. And okay. So for example, let's imagine this curve that has these control points that in a way, they're not so evenly distributed in space. The first four are very close to each other, but the other two are kind of far away. So what happens is that because the polynomial that defines this curve depends so strongly on the position of the control points, it turns out that the internal distribution of the parameter space, so where each one of the points, is not even. And it's not even because it corresponds also to the density of more or less of where the control points are in three-dimensional space. So if imagine if this curve had a parameter space, a domain that went from 0 at the beginning and 1 at the end, this is not always guaranteed, but let's imagine that that's the case. Then if we start querying the curve for a point at parameter 0, we will get this one. If we get another one for parameter 0.1, we might get this one. 0.2 might be here, 0.3 might be here, 0.4 might be here, 0.5 might be here. But you can see how 0.5 is nowhere even close to the center, just because half of the control points are very, very close to each other. Whereas if we keep going, and now I ask the curve for a point in parameter 0.6, we can see that those points may actually start spreading out and getting farther from each other, as in a way they might be accelerating over the curve. So this could be 0.5, this could be 0.6, this might be 0.7, 0.8, 0.9, and this would be 1. So the bottom line here is the domain of a curve is not evenly distributed in Euclidean terms. So the linear distance between those points is not going to be the same, or the chord segment, so the length of this curve and the length of this curve, is also not going to be the same, even though the distance in the parameter space between them is the same. So you can think of the domain as this number that represents where we are along the curve, but it's not linearly dependent on the curve, and it also has nothing to do with the actual length of the curve. Okay, it has to do with the distribution of the control points. All of this will be a bit more clear in the next videos when I start showing examples of how this works. Okay, I did like that one. So let's go back to what are we doing now? Control points, the domain, and the degree. So I have that, and then I'm going to go back to, well, I'm just going to save this, and then I'm going to say that curves have knots and have other properties, but those are actually not, I don't think they are very interesting myself, which might be a strong judgment call on my side, but I'm going to stick to that. Okay, so I'm going to do this. Okay. So that's going to be a surface, and I'm going to say this is going to be the direction. This is going to be direction. This is going to be U. This is going to be direction V. So any point can be represented, and if we do this and with lines, then we can actually say we can also divide this in a way kind of like that. So I can draw a point anywhere on the surface like that. Okay. Okay. Now, NURBS geometry has a few other properties, such as, for example, knots and other things that are perhaps a little less intuitive. But so I think, and for the purpose of modeling, I consider that they're not so interesting, actually. So I'm going to skip over them to move on to other kinds of NURBS geometry that is not just curves, but is surfaces. And the idea is that all the properties and all the concepts that I just explained for curves, they apply exactly the same to surfaces. It's just that instead of having one polynomial that defines the curve, I have two polynomials that define the curvature of the surface in each one of the directions. So what does that mean? It means that when I have a NURBS surface, what I do have is, first of all, I have a cloud of control polygons like this, which define the overall curvature of the surface in both directions. What that also means is that I have two directions. Just like I had when I was talking about curves, I had this one direction defined by the curve, and I typically refer to as t as where I am along the domain. For surfaces, it's typically referred to that the internal direction of a surface is referred to as the u direction, that's one, and the v direction is the other one. What that means also is that what that also means is that I do actually have domains in each one of the directions. So the u direction might go from a value of 0 here to a value of 1 here. And again, it doesn't have to be 0 or 1, it can be whatever, right? So a value of 0 here to the value of 1 here. And then in the v direction, we may also have a surface that goes from 0 to 1 in the parameter space. What that means is that I can say, well, can you, for a surface, can you, if I have a surface in a parametric model environment, I can say, can you give me which point on that surface is at internal parameters UV 0.5 and 0.5? And then if you get that, it will give you a point that it will be probably somewhere close to the center. But remember that it will definitely not be exactly at the center, depending on the distribution of the control points. If you ask for a point that is in UV coordinates 0 and 1, so for U0, it will be here, and for U1, so that would be the coordinate, the points with coordinates 0.1. This would be point with coordinates 0.5, 0.5. And a point with UV coordinates 1, 1 for this surface will be here. Okay, so this will be 1, 1. But remember, this is internal UV coordinates. Whatever the X, Y, and Z coordinates of each one of those points will be, it will depend on where the surface is in the Euclidean space, how rotated it is, etc., etc. So think of UV as, if you will, an internal coordinate system for geometry. And actually, sometimes we can even add a third parameter, which is the W coordinate. Because if you think that the surface has curvature that is continuous across all the surface, for each point on the surface, we will always be able to find a perpendicular direction to that surface. And then that perpendicular direction, we will be able to define also a distance from that direction, which may give us a point that is offset from the surface at a particular distance. So that would be the W direction. So if you think of it in a very abstract way, a surface with internal UV and W parameters defines a local three-dimensional space that is warped, that is bent, based on the polynomial that defines that surface, which is actually a pretty cool concept if you think about it that way. Okay, so any three coordinates, UV, W, can define a location in local parameter space for a surface, and then depending on where the surface is, how big, etc., etc., that will give us the actual XYZ location of that point in three-dimensional world coordinates or Euclidean coordinates or whatever. All right. So this idea, finding points and using points based on their UV coordinates on a surface, will be a technique that we will use all the time. It's one of the most popular ones when it comes to modeling with NURBS surfaces. Okay, so yes, so that is, yeah, so that's one of the most important concepts that perhaps I wanted to talk about when it comes to NURBS geometry. Now, this may have sound a little abstract, so don't worry. In the coming videos, we're going to see examples, applied examples of how this works and how we use this in software. But before we move on, I just want to point you to additional documentation that is super, super helpful. So I really, really recommend that if you want to learn more, you go to and you check the Essential Mathematics for Computational Design. It's an open source publication that Raja Isa from the McNeil team published a long time ago, and she's been refining it over time. It's a great documentation. It's really easy to read. You can download it for free. And I can see that she actually just created a bunch of YouTube videos to explain all these concepts, which is amazing. And I'm a huge fan of her work. So thanks a lot, Raja, for doing this. But on top of that, as you know, I teach computational design at Harvard University, and I have a series of open lectures of my course on YouTube, and I have one in particular that is called Curves and Surfaces, that where I explain all the things that I have explained in this video in much more detail. So if you're interested in any of this, please make sure you check these lectures. Is my course Introduction to Computational Design at the Harvard University Graduate School of Design. And the lecture in particular is lecture 13, Curves and Surfaces. There might be a link to this in the description of the video. So, all right, so this was brief introduction to NURBS geometry, and let's move on to the next video where I'm going to explain now how to create some of these entities, some of these simple NURBS entities in a modeling environment. In our case, it's going to be rhinoceros. And if you like what you saw, consider subscribing to the channel, liking this video, notifications, etc., etc. See you on the next video. Woohoo! All right. Oh, no. I don't want to play the video. All righty. Okay, that was a lot. That was one video. Oh my God. Okay, I need to take a break. I'm going to go drink some water. I'll be right back. Pedro Arasto, how you doing? Good to see you. I'll be right back. Okay, I'm back. Oh, all right. So, what are we doing now? I'm going to just explain, like, record a really quick video in Rhino, just going over basic geometry in Rhino. Okay. Hi, this is Jose Luis, and in my previous video on this series called Introduction to Parametric Modeling, I explained conceptually why NURBS geometry is so interesting and what are the main properties that drive it. So in this video, I just wanted to do a few quick examples of how can we actually model in a 3D modeling environment with non-NURBS geometry and with NURBS geometry. So here I have my Rhino viewport. The Rhino is a 3D modeling environment that is very popular among product designers, sometimes in architecture, but as well, it is very well known for having a NURBS kernel that allows for freeform modeling, which is super interesting. So if I have my UI here, and I'm just going to go directly to full perspective mode by double clicking on the perspective tab here. I can pan by doing shift and right click, and I can zoom in with the right mouse button, and I can also rotate with the right mouse button. So what I'm going to do is for example, here on my tab, I can create points, all right? And then, for example, I can create 1 point. I can right click to repeat the action and create another point, another point, another point, all right? And then what I can do is I can, for example, now take these points, and if you have the gumball option turned on, you will see this kind of like small local coordinate system that allows you to move the point in three-dimensional space. So whatever it was, I'm just going to nudge it up a little bit, something like that, you know, and now I have these 3 points in three-dimensional space. I can also create simple lines. So for example, if I long click here, you can see that I can create single lines. So that's going to be a line between 2 points. I'm going to repeat another line between 2 points. And then if I click on the line, I can move the whole thing. Oops, I can actually extrude it. But I can move it if you just click on the arrow. I can move the line in three-dimensional space. And also, if I select the line and I press F10, what I will do is I will turn on the control points for a line, and therefore I will be able to modify just individually each one of the points. And now I have a line that is curved in 3 dimensions, that is inclined in three-dimensional space. I can also, if I long click, I can select polylines. So I can just click on a bunch of points and have this complex polyline show up. If I click on it, again, I can move it in three-dimensional space, etc., etc. But if I click on the line and I press F10, then I turn on the control points, and then I can start manipulating each one of them individually, which means that now I have given volume to what it was a planar polyline before. I'm going to delete all of this stuff, and now let's get to the good stuff. So I'm going to delete all of this, and I'm going to go to here to splines, all right, and to curves. And then you can see that if I long click, I have a bunch of options to create curves, but the first one is going to be a curve through their control points. What that means is that I can create a curve very similar to the one that I drew. And you can see that what I'm doing here now is I'm clicking the control polygon, and I'm creating the control points of the curve. Right now, this curve is infinitely smooth, and if I zoom in, no matter how much I zoom in, I'm never going to see any kind of discretization, because in theory, this curve is infinitely smooth. Again, it's defined by a mathematical polynomial, so I can find any smooth point on it. If I click on it, you can see that the control polygon shows up, and the control points that define it also show up, which means that I can take this point, for example, and I can move it like this, and you can see how the curvature just adjusted between that and that, you see? Or I can, for example, just move this one here, I can move this one here, or I can even move them in three-dimensional space so that the curve is not planar, but has some volume, you see? And then you can see how the curve is now a very smooth three-dimensional curve defined by the control points, right? Now, for example, what if I wanted to change the degree of the curve? Well, when you create the curve, when you click on creating the curve, you can see that before you start, it gives you the option to choose in the degree here. And by default, it's degree 3. So let me see if I can create 2 curves that have the same let me see if I can create 2 curves. So that's going to be, I'm going to create 6 points here. And then I'm going to create a curve through control points of degree 3. And I'm going to snap to these points. So I'm going to make sure that I have object snap turned on here on the options. Oops, sorry, let me escape here. I'm going to turn object snap, and I'm going to click on point. And I'm going to make sure that object snap is on, so that when I click here, degree 3, I snap to this point. 1, 2, 3, 4. All right, so that was the curve of degree 3. If I now click here and I say, no, I want a curve of degree 5 now, and I use the exact same points, you can see that the curve that I generated is much smoother. Well, let's do a degree 4. Well, this one, if I use the same point, it's going to be somewhere in between both of them. So you see? So this is degree 3, this one is degree 4, and this one is degree 5. And you can see how all of them have the exact same curvature. What about degree 2? Let's do degree 2. And so this one, you're going to see how the curve is actually tangent to the control polygon at the center of each segment. So this one is control 2 and it's touching. It's actually touching the curve at the center. And if I were to do degree 1, you will see how this will be simply just the control polygon, because it will be an actual polyline. All right, can you see that? Awesome. And now on top of this, there's actually other ways you can create curves. So for example, there is a very popular way of creating curves, NURBS geometry in Rhino, which is through interpolated points. What does that mean? Well, if you remember, for degree 3, 4, and 5, none of these curves is actually touching the original control points. And sometimes, for whatever reason, I may have a situation where I have points that I know that I want to go through. And therefore, creating a control polygon that is guaranteed to go through those points can be tricky. So that's why creating curves using interpolated points is a really good way, because if I click on the points, with this method, I know that the curve will exactly touch each one of those points. However, if I touch, you can see that what Rhino has done is that it has created control points automatically at the places where it knows that if those points are the control polygon of this curve, then that curve will pass exactly through the points that I had specified. So in a way, it's like creating the point is creating the curve the other way around. So instead of giving it the control points, I give it the points that I want to pass through, and then Rhino will figure out what the actual control points of that curve are. All right. Okay, and now I need to move on to surfaces. How am I going to do that? From grid point, straight, loft. Oops, sorry. What did I do? Okay, sorry. So we're going to do surfaces now. How am I going to do that? Okay, I think I'm just going to create a surface and explain that it's typically not the way. We typically don't create surfaces using control points because it's very tedious. What we typically do is we use ways of creating the surface, and then we actually end up getting the control points. So for example, yeah. So I think I was with my mouse open when I ended the video, right? that clip. All right. And then the last thing that I would like to show is how to create surfaces. So for example, because surfaces are defined by a cloud of control points, very typically we don't create surfaces by defining the control points. It's just very tedious. There's a lot of them. So typically the way we do that is by using operations that, starting from curves or starting from other primitives, end up giving us surfaces that have some kind of logic. And therefore, we also end up finding what the control points for that surface are. Very similar to the way we have created the interpolated curve here. So for example, I'm going to delete everything here, and I'm going to say, for example, I'm going to go to this panel and long click it so that we extend all the options. And you can see that, for example, I can have here a surface from 4 corner points. So I'm just going to create 4 corner points, all right? And if I right click here and I say ghosted, I can see a gradient like a shaded representation of this surface. If I click on the surface and I press F10, you can see that the 4 control points show up. This is a very simple surface. It only has 4 control points. But you can see that I can start dragging it. And now that this surface has volume in 3-dimensional space and looks like a parabolic hyperboloid kind of situation, right? So this could be a way of creating a surface. Now, another way can be, for example, a very common way is by lofting a surface. So for example, I'm going to go to the right viewport and I'm going to create I'm still using polynomial degree 1. I'm going to create three curves. Another one like this, and another one like this, for example. I'm going to right click. You can see that they're all in the same plane. So I'm just going to move one of them here and another one farther down. So you can see that now they look something like that. And now what I can do is I can click here and I can click on loft, and I'm going to select the 3 curves, the first one, the second one, and the third one. And as I right click, you can see that I'm given some options, normal, loose, tight, whatever, but I can press OK. And by pressing OK, you can see that I have created a smooth surface that passes exactly through the 3 curves that I had defined. And if I click here and I press F10, you can see that now I have this cloud of control points that define that surface. So in a way, it was a very similar process to the interpolation. I tell Rhino, where do I want the surface to pass through? And then Rhino calculates what are the necessary control points to generate that surface. And after that, I can mess with those points. So I can drag this point up, and you can see that the surface smoothly bumps up. And this one I can also bump the surface all the way up here, you know? And then the surface has now this bump here. And the idea that by dragging in and modifying the control points, I can create smooth variations on the surface of the object, is one of the powers of NURBS modeling. And it's one of the powers that make it so attractive for free-form modeling. Okay? So there are many, many ways of generating surfaces. So if you long click here, you can see that you can do it by doing spliner surfaces from a network, loft, from degree, from edge curves, from patches, but with extrusions, point extrusions, you can do sweeping, you can do revolving, you can do a lot of things. But we will explain more of those in further videos down in this series. Okay? So now, and of course, sorry, I forgot. We have surfaces, and in Rhino in particular, we have this thing called B-reps. B-reps means boundary representation. And what that basically means is just that by stitching a lot of surfaces together, you can create something that feels like a solid object. So for example, I can create a cylinder here, all right? And you can see that this cylinder is basically 3 surfaces. If I click here, you can see, and if I explode it, you can see that it's one surface here, then it's the cylinder surface, and it's the other one here, right? So this is the concept of B-rep. B-rep is just a collection of surfaces, typically that enclosed a watertight space, a space that has no gaps inside of it. And for us, it gives us the impression of a solid object, but it's not really solid. It's just a bunch of surfaces together. Same goes here, so you can do a bit more complex stuff, like for example, you can do a torus, right? And this is also, in the case of the torus, this is actually one surface, which is bent on top of itself. Or for example, you can do like a truncated cone, for example, or something like that, right? Where you can see clearly that is also, again, 3 surfaces stitched together. All right, I think, and this idea, let me do a sphere, for example. If I have a sphere, I can generate a sphere, and the sphere will be this continuous surface that is wrapped around itself. This, as you can see, is infinitely smooth because it's a mathematical sphere surface. If, for instance, I were to create a mesh, for example, let's create a sphere that is a primitive, and I'm going to create it here, right? And I'm going to do the same thing. You can see that if instead of using a brep object, what I create is a mesh, then it turns out that the quality and the nature of the two geometries is very different. This sphere is made up of a series of discretized faces, each one of them being a quad. So each one of them having each one of them being a planar quad made out of 4 edges, right? And then these triangles here on the top. And this is just basically a collection of points and a collection of edges that join them together. It doesn't have any mathematical entity inside of it. It's just vertices and faces joining each other. I will explain a little bit more of this farther down in this tutorial series. Okay? Now, I think this was enough for a modeling introduction to NURBS geometry. Let's take a look now at how do we handle NURBS geometry inside of Rhino. How can we inside of Grasshopper, how can we generate, create, and modify NURBS objects inside of Grasshopper, which is one of the most powerful features that the software has. So let's take a look at that and how it relates to parametric modeling in general. And of course, if you like these videos, consider subscribing, liking the video. Thanks a lot. See you in the next one. All right. Woohoo! How are we doing? Oh, that was tiring. Oh, Josh, thank you very much for those words. Okay, so I think we can do the last video. That should be fast here. That should be fast. All right, so the last video is going to be, so wait, so this was 4.1. This is 4.2, and now we're going to do 4.3 lines, polylines, and splines. Okay, so this is going to be, all right, it's going to go. And then where do I start? Well, I start with bifocals, so that's one thing. And then the example that I'm going to do is I'm going to create 4 points, and I'm going to join them with straight lines, with a polyline, and with a control point curve, and with an interpolated curve. All right, so, and so I'm going to start with a slider, and I don't think we need to do this live. So yes, so here -10 +10, and let's set this at 0, for example, right? And this is going to be x, oopsies, it's going to be x, and I'm going to extend this a little bit, and it's going to be x, y, z, and this is going to be y, this is going to be z, and okay, and then this is going to construct a point. Construct a point. And this is going to x, y, and z. All right. Okay, so we have a parametric point here. And I think I'm going to start there. 4.3 lines, polylines, and splines. All right. Hi, This is Jose Luis, and in the previous video on this series on Introduction to Parametric Modeling, I explained NURBS geometry, what it was conceptually, but I also explained how to use Rhino, a direct modeling environment, to generate these types of geometry in the 3D modeling environment. Now, what I would like to teach you in this video is how to also generate NURBS geometry, but using the visual programming language Grasshopper that lives inside of Rhino, and in a parametric way, in a way that all the parameters that drive that geometry can be controlled manually with our algorithm. So how are we going to do that? Well, as you can see from the previous, and you should know that from the previous videos that in the series, I have created a parametric point that starts at coordinate x, y, and z, and you can see that I can control the 3 coordinates of each one of them and move it in 3-dimensional space. So what I'm going to do is, in this exercise, I'm going to create 4 points, and then I'm going to join these 4 parametric points with straight line segments. I'm also going to join them with a polyline, and then I'm going to join them with NURBS curves. One of them is going to be using control points as the input parameters, and the other one is going to be using interpolation points as the input parameters. Very similar to how I did in the previous video. So the way I'm going to do this is I'm just going to select all of this, and I'm going to copy paste it 4 times. So I'm going to create a second point, I'm going to create a third point, and I'm going to create a 4th point. And because you know that I like things to be neat and clean, I'm going to right away select all of these, press Ctrl G, and then group them so that I can now move them around. And this, if I right click here and I type input parameters, these are going to be all the coordinates of my 4 points. You can see that my 4 points, all of them are overlapping on 0, 0, 0. So right now I'm just going to move them a little bit so that I can have like a bit more of a 3D perception of where they are, if you will, or something like that. And then here, this one is going to be all the way here, and it's going to be in negative. So you can see now that my 4 points are somewhere here in 3D space, you can see, and they form this kind of situation. All right. Okay, so let's start simple. The first thing we're going to do is we're going to join each one of these points, each one of these pairs of points, with simple line segments. The way we can do that is if we go to the Curves tab, and if we go to Primitives, you can see that one of the first one that I have is a simple line between 2 points. Okay, so I can click that one and drop it on the canvas, and then what I can do is I can say, well, the first input point is going to be point A, and the end point is going to be point B. And you can see that immediately I get a pre-visualization here. And as we have seen in previous videos, because everything is parametric, if I change the coordinates of the input points, I will change where the starting point and the end point of this particular line lies. So now I can double click and drop another line component between 2 points, and then send the second line is going to start with the second point and is going to end at the 3rd point. And I'm going to double click again, type line, find this one, and the 3rd line is going to start from the 3rd point and it's going to end at the 4th point. All right. Wonderful. And I'm going to align these guys, distribute them evenly, and group them. And this is going to be 3 line segments that join my 3 points. You can see, and everything is parametrically bound. Everything is driven by these 4 points that can be controlled parametrically and that define these 3 line segments. Okay, this is great. Now, these 3 lines are 3 individual line segments. But sometimes what we want, perhaps, is to have one single polyline that joins the 4 points that I am parametrically modeling. So if I go to Curves and to Primitive again, you can see that somewhere, not in primitives, but this case in splines, we can find the polyline component. Okay, polyline, as you can see from the description, creates a polyline connecting a number of points. So what I'm going to do is, first of all, I'm going to select all these lines and I'm going to right click, I'm going to middle click and disable the pre-visualization. Or actually, you can do Control Q to disable the pre-visualization so that they don't show up here and I can see what's going on. You see that they turn dark gray. We've seen this in previous videos. So now what I'm going to do is I'm going to use these 4 points to feed into the input of the component. The component has an input that is called vertices, and you can see that the description says that it's a list of vertices, which means that I have to plug in all the vertices in this same input. And then this has another input that says whether if I want to make the polyline closed or not. And this symbol, the symbol with a circle and a half moon inside of it, means in Grasshopper terms, it means that that parameter is a Boolean. Boolean means something that can either be true or false. So I will show you how that works. Okay, so in the vertices, we need to plug in the points for the polyline as a list. So if I start plugging in the first one, and then I plug in the second one, you're going to see that the second one snaps the first one out. And if I do the third one, you're going to see that it snaps the second one out. So this is now good, okay? Because what I need to do is I need to plug them all together in here. So what I'm going to do is I'm going to plug in the first one, and then in order to make sure that the second one also adds in without snapping anything out, I'm going to make sure that as I join it, I press the Shift button. You see how my icon turns into a green arrow and a plus sign? That means that I'm going to be adding an input here. So I have added a second input, and then here I'm going to press, as I press Shift, I'm going to add a third input, and here I'm pressing Shift to add a fourth point to the list. You can see that I have now connected the 4 points to the same input, which is great, and which gives me a polyline object, a polyline curve here coming out of this. And if I click, you can see that this all turns green. This component now has a polyline. I may want to choose to close the polyline or not. Closing it means that there's no open gap here, that it will always wrap up into the first point of the polyline. And I have to feed it a value that is true or false. So how do I do that? If you go to parameters and you go to inputs, you can see that just as we have sliders for numbers, for inputs, we can have a Boolean toggle. A Boolean toggle is basically something that I can double click to make true or false, true or false. And if I right click here, I can say, is it going to be closed? And then if I plug this in here, I can see that it's not closed, and now it's closed. And you can see how this new segment shows up. Not closed, close. Not closed, close. I'm double clicking on the Boolean toggle. Boolean toggles are like sliders, but only for true and false values. So, okay, so now I have a polyline, and probably I may want to bring my parameter here. So I'm going to select everything, and I'm going to right click here. I'm going to make sure that I'm going to make sure that this gets added to the group, okay? It's typically very, very good practice to keep everything that is a parameter, that is something that you want to work with, at the left end of your definition, okay? And everything that shouldn't be messed up just on the right-hand side. Okay, so I have my polyline, and now what I want to do is I want to use these 4 points to create, I want to use these 4 points as the control points of a NURBS curve. The way I can do that is by going to curves, going to spline, and then seeing that here I can create a NURBS curves. And you can see that the description says constructs a NURBS curve from control polygons. So I'm going to click that, I'm going to drop it in here, and I'm going to take a look at the inputs and the outputs. This is a very good thing to do anytime you are new to Grasshopper. You want to take a look at the components and see what they're asking you for and what they're giving you. So for example, V tells me that I need the vertices, the control points, as a list. So that means that I'm going to have to plug in here all the points. So I'm going to just do it. The first one, and then the second one with the Shift pressed, the third one with the Shift press. Oh, I plugged it in the wrong way, so I'm going to do Control C to undo. The third one on here, and then the fourth one with the Shift. You can see that if I click here, this curve turns green, which means that this is the visualization of a NURBS curve that uses those 4 points as their control points. And of course, again, if I change where those points are, like everything updates correspondingly. Everything is parametrically bound. Let's take another look at more inputs. If I look at D, it says that it's the degree of the curve. And the degree has to be, according to the icon, has to be an integer value, a number that has no decimal part. Curves, NURBS curves cannot have a degree that has decimal part. It has to be an integer. So how do I do that? Well, I can create a slider here, number slider, and if I edit the slider, I can make sure that this is a natural number with minimum being number 1 and maximum being number 3. Because remember, since I have only 4 points, for this particular arrangement, I cannot have a degree larger than 3. So I'm going to put this in here, and now if I turn this off, you can see that I have my NURBS curves is now degree 1, degree 2, so that is touching the control polygon here, and then degree 3, which is smoother. Degree 2, degree 1, degree 2, degree 3. So this is exactly what I was explaining before. If we had more control points, we could try out degree 4, degree 5, etc., etc. And then what about P? P is periodic. Periodic is a fancy term in geometry to just say whether if the curve is going to be closed or not. So what we can do is, and you can see that it's a Boolean. So what we can do is we can plug this same input here and say, do we want to close? Yes. So this is a closed NURBS curve in these 4 control points. And look, if I do degree 2, it actually becomes tangent to the control polygon. And if I do degree 1, it just becomes a polyline that is closed. And if I open it up, then it goes back. Okay. And then for outputs, we have the resulting NURBS curves, and you see the icon is a nice NURBS curve. If you say L is the curve length, which is apparently 11 units in Rhino space, and D is going to be the domain. Turns out that this curve happens to have a domain from 0 to 1. This is actually really rare for curves, but yes. So so we can plug in a few more panels here, and this is the length, and this is the domain. And I'm going to align and redistribute, and this is a NURBS curve. Okay. So this is very interesting. The component is not only giving us the curve, but a lot of information about that curve, which could be useful down the road for other operations. And last but not least, let's take a look at using these 4 points to construct an interpolated NURBS curve. The way we do that is I can go to splines and I can go to interpolate, which says create an interpolated curve through a set of points. I'm going to drop this here, and you can see that I have a lot of stuff here now. The input is the interpolation points, so I'm going to plug in my vertices. So 1, and then the second with a shift, the third pressing the shift, the fourth pressing, what am I doing? The fourth pressing the shift, and you can see that now the curve has appeared, and it has is going through all the points. You can see that if I zoom in here on the other inputs, I also have a degree input. So let's plug in here and let's see what an interpolated degree of curve of degree 2 looks like. Okay, which looks very similar to me, because I guess it has to be degree 2, because it cannot be less than degree 2. Interpolation does not allow even degrees. Okay, so this component does not allow even degrees for some reason. And then P is whether if the curve is periodic or not. So we're going to plug this in here, and then we're going to turn it on, and you can see how the curve does this. I'm going to turn the other one off. You can see how the interpolated curve does this weird egg-shaped kind of kinky thing here, which is kind of interesting, actually. Oops, I think where am I? Where am I? Oh, I got lost. All right. Oh yeah, because it does this weird twist because of how the points are in 3D space. Alrighty. And then K is called the knot spacing, which is a way of, this is very difficult to explain, it's a way of distributing how the tangencies of, not the tangencies, how the domain is distributed across the NURBS space, more or less, but not really. Anyway, if you want to control this, you can add here a number so that you change the type of knot style to uniform, to chord, or to square chord. All right, and the outputs are going to be, I think, pretty much the same. One is going to be the curve, the other one is going to be the length of the curve, and the other one is going to be the domain. And you can see that the domain now is from 0 to 24 point something something. All right. Okie dokie. So these are the 4 ways we have of creating curves. For example, we can, between 4 points, we can create straight line segments, we can create polylines, we can create NURBS curves from control points, and we can create NURBS curves through interpolation over those points. All right. Wonderful. So this is great. And I think this was a good introduction to simple generation of curves in Grasshopper. Now, what I would like to take a look at now on the next video is how to, for example, having these 4 points in Grasshopper might be a little tedious, and sometimes working with coordinates, depending on what we're doing, can also be a little tedious. So I would like to show you in the next video how to work with, instead of using parametrically generated geometry as inputs to generate form, how to create actual geometry that is coming in from Rhino to generate form. So stay tuned for that on the next video, how to import Rhino geometry into Grasshopper. And as usual, if you like what you saw, consider subscribing to the channel, liking this video, etc., etc. Thanks a lot. See you on the next video. All right. Woohoo. Okay. So I think that's going to be it for this morning. I have a meeting that I have to jump on right now. So thanks for being here. Any questions, comments before we jump out? Otherwise, if you don't, we're going to be streaming again in 2 hours. So at 2 p.m. Eastern time. And we're going to take a look at importing Rhino geometry into Grasshopper, and then how to create NURBS surfaces, for example. All right. And then after that, we're just going to do a few exercises. Any questions, comments? All right, folks. Well, then it was a big pleasure. Thanks for being here. I appreciate doing these things in the company of fellow interested people, and I appreciate your support a lot. Thank you very much, and I'll see you in a couple hours if you fancy more intro to parametric modeling. Bye-bye. Thank you.